Hello and welcome back to another video with It's Dr. Dan, and today we're going to be looking at precipitation reactions, which more specifically occur in aqueous solutions, so in the liquid phase. So when it comes to looking at these, what exactly do we need to remember? What do we need to know? So the first thing is we have to be aware of how different solutes behave in the solvent of water. Meaning that if we're looking at different aqueous solutions where the solvent is water, what exactly happens when are they mixed in? Is it something that is soluble, meaning that it breaks into its ions, therefore leaving it open for reaction? Or is it something that is insoluble that separates from the individual solution and actually makes a solid as a result? So that's what we're going to be trying to look at here is something going to be a solid, or is it going to be aqueous going through those two individual types of reactions here? So when we have two different solutions, what can happen is we are always trying to figure out what is the actual chemistry within a reaction. Can we illustrate it? Because in a lot of double replacement reactions, you have multiple solutions mixing together, and it's not always obvious where the actual chemistry is occurring. Sure, you mix these things together, but you have multiple ions that are participating in the reaction. So how can we show that? Well, precipitation reactions, you will see a solid form. So, and that's from when you mix two aqueous solutions. So one of the things that we're going to be looking at is, all right, well, if we have, let's say, these two individual vials here, even though they're both aqueous when they are separated, well, what happens when you mix them together? Let's say we put them in the same test tube. Is it going to precipitate out? And sometimes you're going to see that. You might have a solution that are completely clear, and all of a sudden, like magic, and just like in the instant, you have a solid that forms. So that's something that we're going to be looking at step by step on how we can see these. So how do we do that? How do we do these kind of problems? So the very first thing that we're going to do is, if I have the following problem here below. So it says we have iron 3 nitrate and sodium hydroxide. So I have here drawn, I have iron 3 nitrate drawn on the left, and you see that it's dissolved. Notice how the ions are apart. And then we also have sodium hydroxide over here, where the hydroxides are separated from the sodiums. They completely dissolve in water. What will be the net ionic equation if you mix them in an aqueous solution? All right, what does that mean? So what we're going to be doing is step by step on how to get to net ionic equations. So if we have a net ionic equation, how do we show it? So let's try to go about doing that. So the very first thing we need to do is write out and convert the names here. So looking at this reaction, we have iron 3 nitrate and sodium hydroxide. These are the two things mixing together. So if we remember from naming, we have Fe for iron. It has a Roman numeral 3. So that tells you that it has a charge of 3+. Nitrate is one of our polyatomic ions. So that's going to be NO3-. We have to, being that these are separate ions, we have to swap drop them. So if we do that, we swap drop their numerical values. This is going to lead to us having Fe with a nitrate on the other side, with 3 individual nitrates all around iron. Now the other one is sodium hydroxide. So this is going to be in addition to sodium hydroxide, and what we're going to be seeing is how do they actually react together. So this is our reaction, and what we're going to do is step by step, how can we do that? So first step, get the names. Sometimes you don't always need that step, but sometimes we have to. It depends on the difficulty of the problem. The harder problems are going to make you do that. The easier ones, not so much. All right, now let's predict the products. So with most aqueous reactions, it's going to be double replacement or double displacement reactions, about 99% of them, which is really nice. That means we don't have to try to play this guessing game of what is the recipe for figuring out what type of chemical reactions. So we have the following, right? We had iron nitrate, and that is mixing with sodium hydroxide here. And this is going to be a double replacement reaction. So being that is the case, we're going to do AB plus CD. So we'll label our species. So every cation and anion gets a label. So iron would be one, nitrate would be the other, sodium is one, hydroxide is the other. So being that the tip here is inside outside, the inside bond together, and then the outside bond together. So what exactly would we get? Now, being that we have to predict the products in this type of reaction, we have to make sure we are writing down what ions we are creating. We're only looking at the ions. So being that we'll have iron 3+, that's going to be mixing with hydroxide, OH minus, and then we're also going to have sodium plus and nitrate minus mixing together. So these are going to be our parts here. So we predicted the reaction, we have our products, but are we finished here? So our next step is we have to do the swap drop on all of our products. It's only the individual ions that are mixing together in solution here. So what we're going to be checking is all right, well, if I have my first one here, so we'll just write them down here. We have Fe 3+, OH minus. We'll take the 3, cross it, the 1, cross it. So what we're going to end up getting is iron with just one single iron mixed with 3 OHs to balance out the iron. So the whole idea here is that we have a 3+ and then 3 individual 1 minuses to balance out both sides of that reaction. Now let's try the same thing on the other one. So on the other side, we have Na+ with nitrate NO3 minus. Notice how the same thing here is we have a +1, -1. It's already balanced. We don't have to do anything else with it. We actually do not have to swap drop this one. Being that it is a +1 and a -1 charges, they are balanced in terms of charges. So let's fill all that in. So we had FeOH and it has a 3 next to it, and then the NaNO3. Now the next step mentions to go through and balance it. So if we're going to balance our reaction here, one thing we have to double check is looking at all of our different species that we have here. Do we have the correct amount of polyatomics, of individual ions? Is it balanced? So one of the big tricks is here is let's start with the polyatomics. So one thing you're going to see is that on the left-hand side of the reaction, we have 3 nitrates on the left, 1 nitrate on the right. So how can we go through and easily balance that? Well, we got to add subscripts. So if I go through and put a subscript on the right-hand side next to sodium, this is going to multiply my number of nitrates by 3, therefore causing my nitrates to be balanced. Now, in the process, it also takes it and multiplies my sodiums by 3 as well. So there's 3 sodiums on the right-hand side, and there's only 1 sodium on the left. So how can we try to zigzag going back and forth? We can put a 3 on the left side to balance that. As a result, that also adds 3 OHs, which it's already balanced on the right-hand side, and one thing you'll see, iron's balanced too. So we have to do many different steps in this reaction. We have to predict it, write out our ions, and balance it to try to go through our reaction. All right. The next step in our process here is to actually use the solubility table to determine what is soluble, what is insoluble. So when we do that, this is actually going to allow us to write out all of our different pieces that we have. So if we have our equation here, why don't we rewrite it for ourselves? We'll clean it up. So we have FeNO3, 3. Now in the original problem, it told us this was soluble. So that means that this is already aqueous in that case. Then we also had that we had 3NaOH. That was also aqueous. And then that was mixing with FeOH3. We need to look up the solubility of that. And then 3NaNO3. So let's take a look and see what is soluble, what is not, using the solubility rules. So we got to take a look at our original equations and try to identify what is. So in the both ingredients, we have iron hydroxide. If this is soluble in water, so going to my previous video showing solubility, this would make Fe3 plus with 3OH minus. The other species would be NaNO3. If mixed with water, would make sodium and nitrate. So let's look at the first one. Is iron or hydroxide, are they soluble? So when we're looking at these tables, we need to look for the common ions. Hydroxide is a very normal polyatomic. One thing you see that it's right down here at the bottom, it's something that is insoluble for most compounds, except when it's bound to calcium, barium, strontium. This case, it's bound to iron, so this is an insoluble reaction. So this would not actually form here. We would not get these ions. So this is going to be insoluble. So we'll write that here, meaning that iron hydroxide is going to be a solid. So we'll write a little S next to that to tell you that this is a solid. Sodium nitrate, on the other hand, this actually goes under our ANA abbreviation, meaning that both of them, alkali metals, are always soluble no matter what. So we can see that here, and so are nitrates. They're both soluble all the time. So in this case, these are aqueous, so we can actually show that these are going to be making ions. So this would be our answer here, for at least for this. And what this is called is our complete molecular equation, is what we have up above. So we're labeling all the different states. So you have to label label the states, balance it, go through all the different pieces. That is what this is called. That is a complete molecular equation. Perfect. However, it was asking for the net ionic equation. So how do we get there? Let's copy and paste what we have here and go to our next step. All right, the next step, step 5. So with this, the whole idea is all right, if we take this, we need to see what dissociates between the reactants and the products, meaning what actually makes ions. So from before, one thing that we could actually see here is that, okay, well, we had all of these different, everything on the left-hand side was aqueous, so they're all going to break down into ions. And then we have all of the products, most of them will break it down into ions as well, except for anything that has a precipitate or a solid, and a gas. So we're going to write down all of the ions. So on the left-hand side, iron nitrate breaks down into iron 3+, and 3 nitrates. Then we'll also have sodium hydroxide. So we have 3 sodiums, 3 hydroxides. Notice how I'm carrying out the coefficients here. So being that we had a coefficient of 3 for sodium, that gets carried out across the entire thing, but it's dissociating, right? They're all 3 of those molecules of sodium hydroxide are breaking apart. So the next one is iron hydroxide. So when that breaks apart, that we found out that was a precipitate. So that stays. It stays as FeOH3, and that's going to stay as a solid. All of these other species on the left-hand side, these are all going to be aqueous. And for most chemistry classes, you have to label that as AQ to show that it is dissociating. Then we have 3 Na+ and 3 nitrates, and both of these are also aqueous as well. Okay, so both those have your AQ next to them to show that those are breaking apart. Now, are we done? So what this is now has a name too. This is the complete ionic equation. So this is showing what is an ion, what is a precipitate in our formula. And really the thing that we're trying to figure out is really what is the reaction occurring. One thing you're probably going to take note of is it's going to have something to do with the formation of this iron itself. How can we actually form this? So this is a complete ionic equation. Now, the idea is here is what we now want to do is our final step is write out the net ionic equation. So how do we do that? So the way to show that is by canceling out spectator ions. So what is a spectator? Well, if you go to a sporting event, we are spectators. We are not participating in the actual event. We are just watching. We're not actually doing anything. We're just enjoying it. So what would be happening here is if you have spectators. So what we do is we look at both sides of the reaction and see where are there spectators. For example, notice how there are 3 nitrates on the left-hand side, 3 on the right. It's on both sides of the equation. So cancel out same ions. And it has to be an ion, an individual ion too. And it has to be both sides. There's one other individual ion that you might see, and that is if we see Na+, right? That's on the left and also on the right. So that goes away. Now the net ionic equation is whatever is left over. So the net ionic, and in this case, we have Fe3+ aqueous plus 3 hydroxide, also aqueous, yields the precipitate FeOH3, and that is a solid. And that is our final answer in this problem. So that is our net ionic equation in this particular reaction. So we had to do a lot of work. It takes all your former skills to really go through it and try to figure out what is your net ionic reaction. So what if, just one quick little example, what if you had the following? So here I have sodium nitrate and and ammonium chloride reacting together. Notice how both of these species, or everything here, is something that is soluble, meaning that these are both aqueous. They follow our ANA rule. So ANA is alkali metals. So we have our alkali metals here. So this follows it. Nitrate follows it. Ammonium follows it. They're always soluble. If this is to happen, where you have an example where if we do inside outside, meaning that both of the products are completely soluble. So if this is to break down into all of its ions, when we write the ionic equation, what is the answer in terms of this reaction? Well, being that everything here is an ion, everything cancels out. So if that's the case, well, if all of your individual ions decide to cancel out completely, so all the chlorines are canceling, all of the sodiums are canceling, all the ammoniums are canceling, when that actually happens, well, that is when we have a complete no reaction. Okay, so whenever everything is soluble, that means that no reaction actually occurred. There has to be something formed. So in order for a reaction, we must either have a precipitation reaction or we have to have a gas evolution. Something needs to happen in the reaction. So keep that in mind. You can have it where everything is soluble and it all cancels out. So this is my video on how to do net ionic equations. I hope that this helped. Please feel free to hit that like and subscribe button. I hope to see you all for future videos, and thank you all so much for supporting the channel and more videos to come, and as I try to improve and making these better. All right, and I'll see you all later and have a wonderful day.